Okay, I hope you can hear me. Yes, thanks everybody for giving the opportunity to talk to you. So today I'll speak about transpiling policies to secure computation circuits. And I will, in the beginning, speak a little bit about why this is necessary, why we ended up doing this, and yeah, then introduce you to how we did this. So a quick word on secure computation circuits. So there are multiple secure computation techniques that are coming up, which are still researched. So you have FHE, for example, you have MPC, and you have zero knowledge. So just to give a quick word on this, so in FHE you typically have an encrypted data, and so a ciphertext as input or two ciphertexts as input. Then you sort of perform a computation on the ciphertext in the encrypted space, and you usually output a ciphertext. Then in MPC you also have input privacy, where multiple parties provide their input, which is kept secret, and then typically the result in form of a signature or something is then just shared. You can also output encrypted values. However, most of the MPC's computations, they output some value that can be public. And then you have zero knowledge as a technology where it's sort of the subset of MPC, where you have just two parties and where only one party has some private input. And then this talk will now just look into this domain of zero knowledge. Let's quickly look at zero knowledge application fields. Because where is zero knowledge applied today? So it's used for creating confidentiality, so credentials, or you're trying to build privacy or anonymity, that falls in this domain. You're using proof systems for creating credibility. So you're showing that for example, a machine learning model has been trained with a specific data set, or you are trying to create credible data provenance. So that's the topic we're talking about next. And like proof systems, specifically snarks, are also used to create compression and use compression. So this is used in a blockchain context in form of roll-ups, because blockchains consume money in the end for doing some sort of computation, and it's good if the computation is minimal. So that's why you're using snarks, and this allows you, instead of to recompute a computation, just verify a succinct proof, and then end up with some cheaper fees. The thing is not working. I want to go to the next slide. Yeah, no. Okay, perfect. So now let's look into what data provenance is. So this is one of the research fields I was contributing to. So we contributed to data privacy with our research to data provenance. And so what is data provenance? So we looked at data provenance in the web, specifically the TLS protocol. And the question is, how can you verify where data originates from and has not been tampered? So typically what you do in the web, this is also what you heard of oracles probably, this is the same thing. So usually in the internet you have a client and a server, and if the client fetches some data, it cannot convince a third party that the data is correct, because the client could just present some fake data, and there would be no possibility for the third party to verify if this data is correct. So one option would be that the server itself signs the data and provides some content signatures. However, there's also this opportunity to run data provenance protocols, where you include another verifying party that intercepts the transcript of the session without getting access to the private data that is shared within the session. Then typically the verifier confronts the client with a challenge, where ZK proofs or proof systems are generally used. And then if the client can prove certain things about this transcript, then the verifier attests to the data, because the verifier can make sure that nothing has been tampered and that the data that the client is sharing actually really comes from this server. And so we in one of our papers, we built a solution and actually try to put this into the world. And here on the right side, you can see the first thing we were building was to create some provenance proofs of the PayPal API. And we gave users the opportunity to create these policies, so select some specific thing they want to compare to and the value they want to compare to, and then prove that they own a PayPal balance that is above or below a certain threshold that they can do. However, like this is now just a fixed and static thing, and behind this challenge, there's a fixed circuit, and we want to make this more dynamic. And the problem is that even for a simple statement, you have quite complex circuit. And this means if you're increasing this policy, so if you, for example, let the user pick different things, different data sizes that they want to prove, different things they want to compare and get credibility for, then this policy will be much more complex, and then in the end the circuit will also be much more complex. And so in order to prevent manual composition and writing of these circuits, we are trying to now propose this transpiler architecture where you just have a new form of policy that's in the best case connected to the UI values, and then you can just transpile the circuit, so all the stuff that you actually need, and facilitate and get more dynamicy into this application. So now just a few words on the background. So zero knowledge proofs, I talked about it. So it's a proof system. So between two parties, so a prover can convince a verifier of a certain computation that this happened by just by computing a proof and sharing this proof with the verifier. And for computing the proof, there is typically some private input and some public input. The public input is usually something that can be publicly shared and does not disclose anything on the private input. And the circuit is typically then creating this connection between the public input and the private input. And there is also some further policy usually evaluated, because users want to show that they possess some private data, but they also want to show that this private data complies to a specific statement. So that's what this function at the bottom does. Next, we go to a transpiler. What are generally transpilers? So they are source-to-source compilers. And in this case, we have a high-level policy language, and then we also have a high-level language of a zero-knowledge circuit that we transpile to. Because with this specific representation, we can use, again, other software to then, I'll show this. So if this main part right here is the transpiler, we get the constraint-based ZK circuit in another language, and then we can use ZK frameworks such as Gnag and whatever to then compile this and actually compute the proof, verify the proof, or even create some solidity code for the verification of the proof. And so what we did is we created now a new policy language and a gadget library. We read those files in and then used a template engine and a specific circuit model to then like transpile whatever custom policy comes into the specific ZK circuit representation, such that this can be then used in these other ZK frameworks. So also one other thing that I want to say, if we look at ZK circuits, so typically these encryption functions and security functions that connect public and private information are quite complex. So that's why we typically have gadgets in ZK circuits, and we just compose different gadgets to come up with the final logic that we need in the circuit. So that's why we also have a gadget parser, and we just focus on in the policy language, you just focus on input to output relations to make it really simple. So here the main goal was to get a really concise representation of the policy. So we just focus on value relations of private and public arguments, and we can add some constraints. So here we say, okay, this is a private argument. So for example, that's your age value. If you don't want to disclose that, we specify a gadget that protects it. So this is a security algorithm. We just need to know the name and nothing else. And we have a public argument. And then here the constraint shows with this greater than what we actually compare. And with this input into our transpiler tool, we then get the ZK circuit. And so we also abstracted the gadgets we use in our library. So we just focus on input-output, in inputs and outputs that the gadgets have. We abstract this away because this allows us to connect. Actually, if you define a private argument, you can, or a public argument or an argument generally, you can connect it to these parameters that you have in the algorithm, so either to the input or output of the algorithm. And this allows you to compose sort of multiple things. And then you can actually, based on the policy representation in the UI, you can then translate this to this ZK policy and use this to dynamically create a new circuit. And you don't have to then, for example, like here we just have these APIs that are supported. So we have ZK circuits supporting these APIs. But like if there will be new endpoints, if there will be new cipher suits or whatever, or even then the policies change, then you need dynamic creation of these circuits. Otherwise, you have to manually do all this. So we have these two components, and with that we get an improved representation of in lines of code. So typically would need to write lines of codes in a circuit of, for example, a TLS commitment of 975, and with the policy we only need to write 22 lines of codes, and like this is the transpile time to get the same circuit, and this gives you just some simplicity and reduction to the thing that you're trying to solve. So our work will be presented at ICBC. We also have another work on identity, so about time-bound and replay-resistant proofs. So the information, you can find this on inzn.com. You can hire me because I'm finishing up right now. And yes, you can find all the information there or at the Embedded Systems and IoT group at Sebastian. So you can check the TUM websites, but I'm also linking this on this side. And yes, thanks for your attention.
There's Florian with a question.
Yeah, thank you very much for the informative talk. So you mentioned as the result so that the source code size shrinks, which is clear if you transpile. What's the effect on the execution time, which seems to be the limiting factor? Does it blow up so that people now use abstractions and they don't know what's happening, or is that not an issue that could happen? So they don't know what the transpiler will do out of it.
Yeah, so right now the transpiler is very simple. So we have not explored that yet. So the thing is that we are still transpiling policies to very simple circuits. So the composition is still rather limited, I would say. But of course you can take the transpiler to hopefully then in the right way connect gadgets together. So this would also for example, help reduce errors in building even circuits. But the circuit that you in the end have has the specific performance. We just create the same circuits and the performance remains the same. However, if things get really complex, and so you have a really complex circuit that has been created manually, maybe the composition can be done a bit differently with the transpiler. So maybe the transpiler could even come up with a way of connecting inputs to outputs, or even pick different algorithms for a specific thing they're trying to solve.
And that was my second question, yes, because somehow you said there is the thing, and yet the signature looks like this, and the implementation looks like that.
Yes.
So, are there chances? I don't know. I'm no expert. So, like compilers, were typically a little bit smarter, and they say, I don't look at individual elements, but there are options to, I don't know, use associativity or other properties of a source program. But that's not. It's really one-to-one mapping it's
Right
not-
now, yes. So
Okay.
the thing is, like inputs and outputs, they even have to be translated sometimes, the representation. So that's something the transpiler must do.
Okay.
So we have to even then switch from, so it depends on what kind of values you're putting in. And these gadgets allow only certain input parameters, for example. So that's something that you have to consider. But then depending on how powerful your gadget library will be, so for example, you could have gadgets that could be labeled as like gadgets that add credibility, some gadgets add like security in form of confidentiality, or some gadget could even be used to I don't know, do something else. So it depends on what the gadgets do. And then based on what you're trying to build or trying to prove, then you can just maybe you are trying to get certain gadgets and then find some replacements if the gadget library has some different things, and then this way find optimized ways. But you still have to, in the policy right now, you still have to specify what kind of algorithms you want to use. Like we don't at the moment like if the other way would be to just let the user input private and public arguments and say they want to get a hiding connection like that, something like that, and then we could pick whatever algorithm we think is best suited for this. Just a hiding property, for example. However, if you want something more, then of course you would need to pick a security algorithm that provides these additional features. So there's a lot of things to do. That's just the beginning.
Okay, cool.
Yeah.
Thank you.
There is another question.
So I had a question on the provenance part that you mentioned.
Yeah,
the TLS.
sure.
So there, how do you actually get hold of the transcript as a, so like how do you do this in practice? Like how would you deploy this? The verifier would have to, how would it tap into the session or the
Yes. So like we have two papers that optimize existing oracles. So the one Origo and the one Janus. And so this is not something we came up with. Like there are other protocols that do the same thing. Like the most simple way is to instead of having the two-party session, TLS session, have a three-party TLS session where the verifier is part as the third party. So this means you have actually the secret that is used. So every party in a, like if you have a handshake session in TLS, both parties have some secrets and to establish this session. And in this case, the client secret is shared between these two parties. So this means the client does not have the full secret and the verifier has the other part. So what you typically do is the verifier keeps the secret on his side and uses it to audit if the interaction, like uses then secure computation because they depend on each other, so they have to collaboratively now compute the client-side values. And then once you have collected enough transcript values and take these values as a form of commitment, then the verifier can disclose the secret share that it owns, and then the client can actually access the content. Because otherwise you also have to collaboratively decrypt the ciphertext and so on. So this is how it's typically done with these secure computation techniques.
Okay, thanks.